In this lesson, we're going to learn all about annuities. Generally speaking, an annuity can be thought of as a series of payments or investments that are made at regular intervals. For simplicity, we're just going to look at simple annuities. These are annuities in which the payments coincide with the compounding period. For example, if your interest is compounded monthly, then your payments or investments would be monthly as well. Please note, in the real world, this is often not the case, and there is a way to convert, but again, for simplicity, we're going to look at simple annuities. We briefly discussed annuities in Lesson 4 when we learned all about RRSPs. Recall, the last year you can contribute to the Registered Retirement Savings Plan is the year in which you turn 71. One of the options is to use the money in the RRSP to purchase an annuity. The annuity is a financial product that then issues payments to you for a set period of time in your retirement years. In this way, you can think of it like a pension, but it's like a DIY pension, one that you make yourself. There are two types of annuities, future value and present value. We're going to start off by looking at future value annuities first. The future value of an annuity represents the total amount of money that will be accrued by making consistent investments over a period of time, with compound interest. The formula is shown below. Here, FV represents the future value of an annuity. Sorry, there's a small typo here. Future value. R represents the regular payments during each compounding period. Little I would be the interest per compounding period, just like we looked at back in the simple and compound interest lesson. And N is the number of compounding periods. Once again, just like we learned back in the compound interest lesson. One important thing to keep in mind with future value annuities is that these problems always involve calculating how much money there will be in the future by making regular contributions over time. For instance, a student may wish to determine how much money they should invest per month today in order to ensure that they have enough money for university tuition in 4 years. This is actually going to be our first example. Here we have a student at Emily Carr Secondary School who just started grade 9 and they work part-time. This student wants to go to the University of Waterloo for their mechanical engineering program in 4 years. So in other words, we need this investment to be ready in 4 years' time. If first year tuition is $22,000 including books, how much money should be deposited into the savings account each month if it earns 4% per year? Okay, so notice that this is different from a typical compound interest problem because you're not just depositing one principal, you're making regular payments over time. As before, let's calculate I and N. The interest per compounding period is the annual interest rate of 4% divided by the number of times interest is calculated per year, in this case 12. Rounding to 2 decimal places, you should get about 0.0033. That's the interest per month or the interest per compounding period. The number of compounding periods, little n, is just the number of years, 4 in this case, multiplied by the number of times interest is calculated per year. Since we're making payments every month, we're going to compound monthly. All right, and we're all set to use our future value annuity formula. So let's write it out. Now, notice that this problem is asking you for R, the payments. How much money should the student deposit every month in their account? So you have to isolate for the variable R. What are you doing to R? You're multiplying it by this big expression in brackets that I'm highlighting. So in order to isolate for R, you're going to have to do the opposite. That means divide both sides by that big expression in brackets, like this. So you divide the future value by the expression in brackets. Okay, it looks like we're all set. You can start plugging in the numbers. So the future value, we would like to have $22,000 divided by, open up a big bracket. You have 1 plus I. That's to the exponent of 48. Then you subtract 1 and divide by the interest per month. Okay, this is something you're going to have to do on your calculator, and these calculations can be quite messy to do on a calculator. I'd recommend you do it in steps like this. You're going to have to use BEDMAS. Start with brackets. Look inside of the innermost brackets. First on your calculator, you should do 1 plus 0.0033. Your calculator will give you a number. Raise that number to the exponent 48, hit equals, you'll get another number. Then subtract 1 from that number, hit equals, you'll get another number. Whatever that number is, divide it by 0.0033, hit equals, you'll get a number. Whatever that number is, you're going to then do 22,000 divided by that number. And if you do that, you should get monthly payments of approximately $423.75. Okay, I hope you followed all that. If you didn't get this number, just try it again, please. Some calculators might allow you to do it in one shot. I would recommend you do it in steps in the way I described. So seeing as how these numbers were quite realistic, just look at the implication of this. In order to have $22,000 for the time you start university, if you wanted to start saving 4 years ago in grade 9, you should have been making monthly deposits of a little over $400 and keep that up consistently for 4 years in order to have about $22,000, which should cover 1 year of university tuition. Just something to keep in mind. Let's try another one. In this case, we're looking at down payments. In order to save up for a down payment on a house, a young couple deposits $600 per month into an investment account that earns 7% per year. That is considered a pretty good annual rate of return, by the way. And we want to determine the value of the down payment in 5 years. Because we're making monthly payments, we're going to compound this monthly as well. So the interest rate per compounding period is the annual interest rate of 7% divided by 12. And that should give you an interest rate of about 0.0058 per month. As for the number of compounding periods, this couple is saving up for 5 years. They're making monthly payments, so 5 times 12 will give you 60 compounding periods. And it looks like we're all set. We want to determine what the future value of all of their savings will be. So the future value is equal to the monthly payments multiplied by 1 plus I to the exponent n, take away 1, divided by I. In this case, you don't need to do any rearranging. We're looking for the future value, so plug everything in. We're making monthly payments of $600. All right, this is a job for your calculator once again. Follow the same steps I've outlined in example 1, and you should get a future value of $42,911.30, which is a pretty respectful down payment. All right, and that wraps up future value annuities. Moving on to the second half of the lesson, present value annuities. The present value of an annuity would represent the amount of money that's needed today in order to generate some sort of specific income in the future. Here's the formula for present value annuities. It looks very similar to future value annuities, but it is different. Here, PV represents the present value of the annuity. R again would represent the regular payments, but specifically the payments during each compounding period. So these could be monthly payments, they could be annual payments. I again is the interest per compounding period, which still has to be expressed as a decimal, and lowercase n is the number of those compounding periods. Present value annuity problems can be confusing, but here's a quick way to make sure you're using the right formula. Any problems involving present value annuities ask you to determine how much money is needed today for some future payment. So usually they involve saving money today in order to receive payments in the future, exactly like what an RRSP does, which we'll look at in the next example. Alternatively, let's say you need money today, for example, a mortgage. Present value annuities involve taking out a loan today and then you making payments to pay it off over a fixed period of time. Both of these will be looked at next. Let's take a look at example 3. In order to plan for retirement, Massimo would like to collect $1,200 per month for 20 years when he retires at 71 years old. In order to help him do this, he's been making regular contributions to his registered retirement savings plan. At 71 years of age, Massimo plans to purchase an annuity with the money in his RRSP. Imagine that the annuity has an annual interest rate or rate of return of 4.5%. How much money should Massimo have in his RRSP in order to reach his retirement goal? All right, let's get started. So first of all, the interest per compounding period would be the annual rate of 4.5% divided by 12 because he'd like to receive monthly payments. This will be an interest of about 0.0038 per month. As for the number of compounding periods, Massimo would like to collect payments for 20 years, and he would like monthly payments. So 20 times 12 is a total of 240. With that being said, we're all set to use the present value annuity formula. I'll begin by writing it out. Okay, there's no need to rearrange anything. We're looking for present value. So he would like to receive monthly payments of $1,200. Be careful here, you do have a negative exponent. And it looks like we're all set. So here we're determining how much money Massimo would need in his RRSP by 71 years of age in order to guarantee monthly payments of $1,200. Work this out on your calculator. Just to remind you again, you're going to have to use BEDMAS. So I'd recommend working inside of the innermost brackets first. Please add 1 and 0.0038. You're going to get a number. Raise that number to the exponent of negative 240. Hit equals, you'll get another number. Then you're going to have to do 1 take away whatever that number is. Hit equals, you'll get a number. Divide by 0.0038. Hit equals, you'll get a number. And then finally, multiply by 1200. And that should give you a present value of approximately $188,711.08. So therefore, Massimo would have needed to save up this much money during his working years in order to guarantee monthly payments of $1,200 during his retirement years. Just think about it. It's pretty realistic. $1,200 a month, although not much, should be reasonable for someone who is enjoying retirement. Keep in mind, they will be collecting CPP at that point, and they may have other investment income to live off of. So this would be additional on top of the Canada Pension Plan or on top of any company pension plans. If you're someone who doesn't have a company pension plan, then you're probably going to want to contribute more to your RRSP in order to guarantee more than $1,200 a month. Please also keep in mind, everyone, the RRSP can hold investments, so you may not have to invest all of 188,000. It could be less, assuming that your RRSP has increased in value over time due to proper investments. Let's look at a real-world example involving house prices. Imagine Ryan purchased a new home in Toronto for $919,000. Imagine he has enough money for a down payment of $100,000, and he signed a mortgage agreement with the bank that states he must make monthly payments for 25 years at a rate of 2.49% per year. So first of all, what will Ryan's mortgage be? If he's making a down payment of $100,000, That means that Ryan will only have a mortgage of $819,000. Basically just the price of the home, subtract the down payment. The interest rate per compounding period will be the annual rate of 2.49% divided by 12 because we're making monthly payments. That equates to roughly 0.0021. This is the interest rate per compounding period. As for the number of compounding periods, it's a 25-year mortgage and we're making monthly payments, so 25 times 12 is equivalent to 300 compounding periods. Because we need the money today, it's a present value annuity problem. So let's write out our present value annuity formula. Now notice we're being asked to find R, the monthly payments. So you're going to have to divide both sides of the equation by this expression in brackets, sort of like what we did in example 1. And it looks like we're all set. So let's plug in the numbers. The present value, or the mortgage, is $819,000. All right, everyone, that is a job for your calculator, so work it out, please. But you should get monthly payments of approximately $3,682.43. And these are realistic numbers based on rough house prices today and current mortgage rates. So I just want you to think about that. How hard do you have to work to come up with $3,600 every month? It is a lot of money. But here's what I really want you to consider in the next example. You're making these monthly payments for 25 years. How much money does the house really cost you? So the future value of your loan, you're making monthly payments of $3,682.43. If you're amortizing your mortgage for 25 years, you're making a total of 300 of these payments. Please note, I'm not assuming refinancing, which is something that will happen over the course of 25 years, but assuming you lock in at this rate, and if you multiply the two numbers, you're going to get $1,104,729 exactly. But wait a minute, the mortgage was only for $819,000. You're right, but you ended up paying much, much more because you're paying interest on top of the loan. So how much interest did you pay? Take the final amount, subtract the original, and the interest you pay to own your home is approximately $285,729. Just think about that. You pay an extra almost $300,000 to own a home in Toronto. These numbers are fairly realistic. Just think about what you can do with an extra $300,000. Food for thought, shall we say? All right, everyone, so that's going to wrap up our lesson on annuities. I hope you found this enjoyable. Thanks for watching. I'll see you in the next one.